Quantitative literacy. This is the 11.2 notes. We're looking at events that involve not and the word or in them. First thing we need to talk about is mutually exclusive. Mutually exclusive is if there's no outcomes in common. Basically, if something is not mutually exclusive, we're going to have to subtract off the overlap. And you'll see what I mean as I go through these problems. For the first two problems, we're looking at this table here. It's basically saying if I roll 2 dice, the possible sums of their faces are all these numbers inside of here. Oops, sorry. Any one of these. So basically it's saying if I roll a 3 and a 4, that sums to 7, so on and so forth. So it just gives us that so we don't have to look at it ourselves or draw it out ourselves. On number 1, what is the probability that the sum is even or a multiple of 6? Okay, so first thing is how many of these outcomes are even? Well, I'm just going to count all the even numbers in the body of this table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18. So I counted 18 even numbers, or a multiple of 6. Well, a multiple of 6 would be 6 or 12. 1, 2, 3, 4, 5, 6 outcomes of those. But I have to ask myself, was there overlap there? Did I double count any of those numbers? Basically, do they have a highlight and a circle on them? Well, yes, actually, in this case, all of them. I have to subtract off that overlap. So the or is going to mean that I add these, but the overlap actually was all 6 of those multiples of 6. So really I'm adding 6 and then subtracting it. So the number of outcomes that are even or a multiple of 6 is 18. This is probability. Remember, it's preferred outcomes, which is 18, over the total possible. The total number of squares down here is 36. So I have an 18 out of 36 chance, or a half, or 50%, or 0.5 probability. Now, on that problem, yes, it turned out that the overlap was all of them. That's not always going to happen. For example, on number 2, probability that the sum is less than 4. So I count how many numbers are less than 4. 1, 2, 3 numbers are less than 4. Or odd. Okay, so for odd, I'll do circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Go figure. So the or tells me I'm going to add those. But I have to subtract off any overlap. So basically, is there anything I double counted? Is there a highlight and a circle? Well, that happened twice on these 3s. So there were 2 numbers that I overlapped or I overcounted. So that would give me 21 minus 2, so that's going to give me 19. The total possible outcomes that are either less than 4 or odd. I put that over the total possible, which is 36. That one doesn't reduce, so we can leave it. For number 3, we're looking at a deck of cards. On letter A, what's the probability that it will not be a king? Now, we can figure out how many that is straightforward, but I'm going to do it with a little subtraction process here again. There are 52 total. I know that there are 4 kings, so to not be a king will be 52 minus 4, which is 48. So there are 48 cards that are not kings out of the 52. You can reduce that. 4 goes into both of these, and it becomes 12/13 as a reduced fraction. So I have a 12 out of 13 chance that if I picked one card, it would not be a king. So that was the word not. Neither is synonymous with that in this context. What's the probability that it will be neither a heart nor an ace? Okay, so now I'm going to think back to what I did on the dice problem. The hearts, there are 13 because that's one of the suits. The ace, well, there's 4 of those, but I have to ask myself, did I double count anything in that? Yes, I did. I double counted the ace of hearts because I counted it in the hearts section and I counted it in the ace. So there was 1 card of overlap. So I have to subtract it off. So I counted 16 possible cards. Now realize on this one, it says neither a heart nor an ace. So kind of like I did here, where I did the total minus the kings. Now I'm going to do the total minus the heart or aces, which will give me 36. And so now I turn that into a probability. 36, oops, that's a 3. Ooh, that's terrible. Let's try that again. 36 out of a total possible 52. You can reduce that. 3 goes into both of those, I believe. Actually, I think, let's see. Yeah, 3 would go into it. That would be 12 over 21, I believe. No, I'm wrong on that. Sorry about that. 4 goes into both of those. There we go. 4 goes into 36 9 times. 4 goes into 52 13 times. So I have a 9 out of 13 chance of drawing neither a heart nor ace. On letter C, this is either instead of neither. Either a spade, there are 13 spades, or a red card. Red card is, oops, something went awry there, hold on. There we go. A heart or a diamond, well, that's 13 hearts, 13 diamonds, that's 26 cards. These 2 events are mutually exclusive. Spades and red cards, well, spades are black cards, red cards are not black cards. So I don't have any overlap. So I just add these 2 up, which would be 39. Now, I'm not going to subtract this from 52 like I did on the previous problem because the previous one said neither. This time I want either. So 39 cards or either a spade or red card over the 52. You can reduce that. 13 goes into both of these, and it becomes 3/4. Now, if you think about this in terms of suits, this makes sense. There are 4 suits. There are hearts, diamonds, spades, and clubs. If I'm saying that I want either a spade or a red card, I'm basically saying I want a heart, a diamond, or a spade. Well, that is 3 out of 4, technically. So kind of a little easier way to think of that one. On letter D, A diamond or a face card? Well, diamonds, again, there are 13 of those. Face card, that's the jacks, which there are 4 of those, the queens and the kings. There are 4 of each, so that's 12. But I have to subtract off any overlap. These are not mutually exclusive. Let me give myself a little space here. Because that means I double counted the jack of diamonds, the queen of diamonds, and the king of diamonds. I counted them in both the category diamond and face card. So there were 3 cards of overlap. So that tells me there are 22 cards that are either a diamond or a face card. I put that over the total, 52. 2 can go into both of these, and this becomes 11 over 26. For number 4, what's the probability being dealt a 3 of a kind? That's 3 of the same, like 3 jacks or 3 sevens or something like that, or a straight. Well, the first thing to notice is that these 2 events are mutually exclusive. There is no overlap. Because if I have 3 of one type of card, a straight is having 5 cards in a row, like 3, 4, 5, 6, 7. You can't have 3 of the same card if you have a straight. So these are mutually exclusive. If you go back in your note packet to the first section of this chapter 11, there were 54,912 ways to get a 3 of a kind. There were 10,200 ways to get a straight. If I add those up, that is 65,112 over the total possible poker hands, which is that 2,598,960,000 number. This one you would do in your calculator. You would divide those, and you would get about 0.02505310. So as a percentage, you have about a 2.5% chance of either being dealt a 3 of a kind or a straight. For the last problem, has a few parts to it. We have what's called a probability distribution. So Amy plans on spending 1 to 6 hours on her homework. That's what these X's represent: 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours. Now, obviously, yeah, she's not going to necessarily spend exactly 1 hour, exactly 2, but basically anything within the category of a 1, maybe we're saying like 0 to 1, and then 2 would be like from more than 1 but less than 2, that kind of stuff. So the probabilities of each one of these, she has basically a 5% chance of spending around an hour, a 10% chance of 2 hours, so on and so forth. They're not evenly distributed. It looks like her best chances are the 4 hours. She has a 40% chance of spending 4 hours on her homework. We can use this, again, what's called a probability distribution, to figure out each of these individual probabilities. What's nice about these is the probabilities have already been calculated individually, so I don't have to do any dividing on this. The chances of spending fewer than 3 hours, that would mean either spending 1 or 2 hours. Remember that or means I add this. I'm going to add the probability of 1 hour, which is 0.05, and the probability of 2 hours, which is 0.10, which gives me 0.15. There's no dividing or anything because, again, the probabilities have already been calculated individually for me. So she has about a 15% chance of spending fewer than 3 hours. So basically I just said, all right, add those probabilities together. For letter B, more than 2 hours. More than 2 hours would mean it could be 3 or 4 or 5 or 6. So that means I'm going to add the probabilities for the 3, the 4, the 5, and the 6. If you add all of those up, you will get 0.85. She has an 85% chance for that. On letter C, the probability of more than 1, but no more than 5. More than 1, so 2 or 3 or 4, but no more than 5 does include 5. So this time I'm adding the probabilities of 2, 3, 4, and 5. And if you add those up, you end up with 0.8 or an 80% chance. And for the last one, fewer than 5 hours. So fewer than 5 hours could be 1 or 2 or 3 or 4. So I'm going to add all of those probabilities up, which would equal 0.75 or 75% chance. Okay, that does it for 11.2 notes.